All right, next up, we're going to take a look at the reactions of our ketones and aldehydes. And so if we think about a ketone and aldehyde, they're generally electrophiles, right? So let's talk about their electrophilicity. So for example, if we've got our carbonyl, we could draw a resonance structure where we have the O minus and then the carbon positive, right? And so we can see that through the resonance effects, we get a partial positive on that carbon. And then, of course, if we think about the other kind of main electronic effect, the inductive effect, we have a more electronegative atom, that oxygen, pulling electrons away from that carbon, which makes that carbon quite partially positive. And so in general, our carbonyls will react with nucleophiles. They'll act as the electrophile, and the nucleophile will generally attack that partially positive carbon and then kick this pi bond up to the oxygen. If you think about what's going on here, right, we're going from an sp2 carbon that's relatively flat, and so that's why that nucleophile can kind of come somewhat towards the backside, but at a slight angle, and then eventually it becomes an sp3 tetrahedral carbon. In terms of the electrophilicity between ketones and aldehydes, aldehydes are generally more electrophilic. So in general, aldehydes are more electrophilic. And if you think about it, that makes sense. So there's our ketone. There's our aldehyde, where R is equal to some kind of carbon. First off, there's the steric consideration, right? The aldehyde simply has less stuff to get in the way from a nucleophile attacking that carbon. And then if we think about the partial charges, they also help make the aldehyde more reactive. So these R groups are generally carbons, and carbons in alkyl chains are generally electron donating groups. And so you can think about these kind of carbons donating some negative charge. And so if in case of the left, you got 2 donations, whereas on the right, you've only got 1. So the one on the right will be more partial positive and thus more electrophilic. And we've already seen a bunch of examples of carbonyls reacting, but let's just go ahead and review one of them with our Grignard reagent. And remember, this is a really powerful reaction because it's a carbon-carbon bond formation, which is very useful in organic chemistry. So what we have here is our Grignard attack up here. And then we're always going to kick up our pi bond to make this oxygen have a negative charge. After that, we do an aqueous workup, so there'll be a proton transfer, and thus transforming our ketone in this case to an alcohol. Of course, we can attack from either side of either face of the ketone, so you do get a racemic mixture here. One thing to note and to be careful about our mechanisms is whether we're in acidic or basic conditions. So the Grignard, remember, it's very sensitive to any acidic proton, so we're generally run these under basic conditions. If we had, for example, acidic conditions, right? So this is an example of mechanism under basic conditions. Under acidic conditions, some of the steps are a little bit reversed, right? So under acidic conditions, we've got plenty of H plus floating around. And so here, the first step is actually our aldehyde or ketone picking up this H plus. And then, of course, you can draw 2 resonance structures for this one. Right, the one on the right shows that the carbon is really what's positive. And then, of course, we can have a nucleophile come in and then simply attack. Or if you have it going to the one on the left, attack and then kick up. But you see under acidic conditions, the protonation happens first, whereas under basic conditions, the protonation happens later. And both of these reactions, right, and most of our reactions that we learn, it's just a nucleophile attacking our electrophile. And so if we think about what's going on under basic conditions, we have a stronger nucleophile, right? Our nucleophile usually has a negative charge. Under acidic conditions, we usually have a stronger electrophile, right? Our oxygen is protonated, and so it has that positive charge, right? And so almost all of our reactions, the nucleophile attacks the electrophile, and that's only going to happen if both of them are sufficiently strong enough to do the reaction.